Right now, in a lab somewhere, a machine is being built that could break every bank account, every password, and every secret on Earth. Most people have no idea it exists. This isn't science fiction anymore. We're talking about quantum computers. They operate on principles so bizarre, they challenge our understanding of reality, threatening to unravel the very fabric of our digital world. This isn't a distant threat, it's a rapidly approaching challenge that could redefine global security, finance, and privacy. So, what does a quantum mean here? It refers to the smallest units of energy or matter. At this tiny scale, our everyday physics rules break down. Particles behave counterintuitively. Quantum computers harness these peculiar behaviors to perform calculations unimaginable for our current machines. It's a journey into the subatomic world to reshape our digital one, utilizing phenomena that feel almost magical, yet are entirely based on fundamental physics. To grasp the quantum revolution, let's briefly revisit classical computers. Your devices store and process information using bits. A bit is like a light switch, either ON or OFF, 0 or 1. Every digital action is a vast series of these zeros and ones, flipped at incredible speeds. It's a simple, binary world, incredibly efficient for its purpose, forming the bedrock of all the technology we use today. From streaming movies to sending emails, it's all just bits. Now, meet the qubit, the quantum equivalent of a bit. Unlike a classical bit, a qubit can be 0, 1, or both simultaneously. Think of a coin spinning in the air. While spinning, it's in superposition, a combination of possibilities. It only decides when measured. This ability to exist in multiple states is foundational to quantum computing's immense power, allowing it to hold far more information than a classical bit, opening up entirely new computational pathways. Let's deepen superposition. Two classical bits represent 4 states, one at a time. But 2 qubits in superposition can simultaneously represent all 4 of those states at once. Add more qubits, and the simultaneous states grow exponentially. 3 qubits can be in 8 states, 4 qubits, 16. This exponential growth allows quantum computers to tackle problems far too complex for even the most powerful supercomputers, exploring possibilities unthinkable before with unprecedented speed. As if superposition wasn't strange enough, quantum computers exploit entanglement, what Einstein called a spooky action at a distance. When qubits become entangled, they are intrinsically linked, regardless of distance. Measure one, and you instantly know its partner's state, even light years away. Their fates are intertwined, without any apparent communication. This deep connection allows entangled qubits to work together on calculations in ways classical bits cannot, unlocking massive computational advantages through their shared destiny. Entanglement is powerful because it allows qubits to share information and coordinate computations instantly. Classical bits try one piece at a time. With entangled qubits, it's like having multiple solvers who instantly know what others are doing, adjusting without direct communication. This allows a quantum computer to explore many solutions simultaneously, dramatically speeding up the search for answers. It's a level of parallel processing impossible with classical technology, unlocking immense problem-solving capabilities by allowing qubits to collaborate on problems. Combining superposition and entanglement gives us quantum parallelism. Instead of trying one solution at a time, a quantum computer can explore all possible solutions simultaneously. It's like a library where you read every book at once to find what you need. This isn't just faster, it's an exponential leap. For certain problems, quantum computers can find answers in minutes or seconds, where classical supercomputers would take billions of years. Truly a game-changer for computation, it allows unprecedented problem-solving efficiency. Today's quantum computers often look like elaborate chandeliers inside large, gold-plated cylinders. This is a dilution refrigerator, cooling qubits to incredibly low temperatures, colder than deep space, just above absolute zero. This extreme cold minimizes interference and maintains delicate quantum states, preventing them from collapsing. It's a marvel of engineering, keeping the quantum magic alive in a highly controlled, incredibly precise environment. The hardware itself is a testament to scientific ingenuity. These machines are no longer theoretical. Companies like IBM and Google are actively building and operating them, increasing qubit count and stability. While still early, often under 100 useful qubits, they prove fundamental principles and outperform classical machines on specific tasks. This rapid progress signals a shift from theoretical research to a tangible engineering challenge, pushing us closer to a quantum-powered future where these once impossible calculations become routine, impacting various fields. Now, back to the chilling hook, how these incredible machines threaten our digital security. Almost all encryption protecting your online life, banking, emails, secure websites, government secrets, relies on mathematical problems incredibly difficult for classical computers. These problems are designed to take billions of years to crack, making them secure by classical standards. But quantum computers don't play by classical rules, posing a direct threat to this foundational security and our interconnected digital world. One of the most concerning quantum algorithms is Schia's algorithm. Developed by Peter Szia in 1994, it factors large numbers into prime components exponentially faster than any classical algorithm. Why critical? Many encryption schemes, like RSA, get their security from the extreme difficulty classical computers have in factoring these large numbers. A sufficiently powerful quantum computer, with Schia's, could break decades of cryptographic innovation in minutes, dismantling digital protections at an alarming rate. Take RSA encryption, used everywhere: secure web browsing, HTTPS, email, VPNs, financial transactions. Its security relies on factoring two huge prime numbers. For classical computers, finding those factors is computationally impossible in a practical timeframe. But Schia's algorithm on a quantum computer could do it with terrifying efficiency. This means virtually every secure connection, protected file, and digital signature using RSA could become instantly vulnerable, exposing vast amounts of sensitive data worldwide. The implications are staggering. Imagine your bank account, online shopping, and cryptocurrency wallets no longer secure. Every digital transaction, every stored financial record could be at risk. Banks and national economies rely heavily on current encryption. A quantum attack could trigger a global financial crisis, eroding trust in digital payments and leading to chaos as private and public financial data becomes accessible. This isn't just a hack, it's a systemic failure. Beyond finances, quantum computers pose a grave threat to national security. Governments and military organizations worldwide rely on strong encryption for classified communications, intelligence, and critical infrastructure. Imagine satellite communications or surveillance networks suddenly transparent. Countries achieving quantum supremacy first could gain unparalleled advantage in espionage and cyber warfare, destabilizing international relations. This quantum dominance race is a new, high-stakes arms race, with global peace potentially hanging in the balance. Here's one of the most immediate dangers: that store now, decrypt later a threat. Sophisticated adversaries are already collecting vast amounts of encrypted data. They're storing it, knowing that while they can't break it today, a powerful quantum computer in the future will decrypt it all. Sensitive information, from medical records to state secrets, encrypted years ago, could be exposed. The clock is ticking, and the data is already being gathered, creating a quantum time bombs for all our historical secrets. So, what can we do? Scientists and cryptographers are developing post-quantum cryptography, or PQC. These new algorithms are designed to resist attacks from even powerful quantum computers. Instead of relying on problems hard for classical machines, PQC uses different mathematical challenges, believed to remain intractable even for quantum machines. It's a fundamental shift to safeguard our digital future against this emerging threat, a proactive defense being built right now. The U.S. National Institute of Standards and Technology, NIST, leads this effort. NIST is running a multi-year competition to evaluate and standardize post-quantum cryptographic algorithms. They've narrowed down submissions to promising candidates, with official standards expected soon. This standardization is crucial, providing a common framework for everyone to implement these new, quantum-safe protections. The full transition to these new standards across all global systems is expected to take at least 15 years, a monumental undertaking. Even with new standards, the transition to post-quantum cryptography will be an enormous challenge. Think about how many devices, systems, and applications rely on current encryption, virtually everything digital. Upgrading servers, routers, smart devices, operating systems, and countless software applications worldwide. This isn't just a software patch, it's a fundamental overhaul of our global digital infrastructure. The sheer scale and complexity mean it will take years, possibly decades, to fully secure our digital world against quantum threats, requiring unprecedented global coordination. While security is pressing, quantum computing also holds incredible promise. Imagine breakthroughs in medicine, designing new drugs by simulating molecular interactions, or discovering novel materials for more efficient batteries or stronger alloys. Quantum computers could optimize complex logistics, revolutionize artificial intelligence, and solve grand scientific challenges. It's a double-edged sword, full of both peril and potential, offering solutions if harnessed safely. The same power that threatens can also heal and innovate on an unimaginable scale. The race to build powerful quantum computers and simultaneously deploy quantum-safe encryption is one of the most critical technological competitions of our time. Nations and major tech companies are pouring billions into R&D. The stakes are global economic stability, national security, and individual privacy. The entity achieving quantum supremacy first could hold immense power, and an enormous responsibility to use it wisely. This isn't just science, it's geopolitical, shaping the balance of power for generations to come. This isn't just a problem for engineers, it affects everyone. Understanding the quantum threat is crucial for digital literacy. While you might not upgrade encryption systems directly, staying informed, supporting research, and advocating for robust security measures all contribute to a safer digital future. The quantum revolution is here. It brings sci-fi challenges, but also opens an incredible new chapter in human advancement. Our digital reality hangs in the balance, and it's a future we must proactively shape together.